Right. Hi, I'm Martin Maas. I'm a research scientist at Google DeepMind, where I work on machine learning for systems and systems for ML. I've been involved in RISC-V since the early days of the project at UC Berkeley, and I'm currently chairing the J-extension task group in RISC-V.
I'm Cliff Young. I'm a software engineer at Google DeepMind. I worked on a couple of special purpose machines, Antons and TPV1s. I helped out on MLPerf's founding. I'm currently acting chair of the AI ML applications SIG and really enjoying that aspect of involvement in RISC-V, and aside from being a huge RISC-V fanboy. So really glad to be here. Next slide is the corporate fun slide, right? So disclaimer, TPUs do not use RISC-V. We're giving this talk because we want to encourage community discussion, involvement, investment, collaboration. We are not saying anything about Google products and services. Please do not extrapolate in public reports. And thank you. We'll get back to the fun part now.
Right. So there is an increasing interest in AI within the RISC-V community. There have been a number of announcements around RISC-V-based AI accelerators and IP. Here's the announcement from Google on Project Open Secura at last year's summit. There were lots of other announcements as well. RISC-V International is working on AI-related standards now, including things like floating point formats and matrix multiplication. And the software ecosystem on the ML side has also been making forward progress with things like TensorFlow Lite supporting RISC-V. And there's all this momentum, there's all this progress. But despite of all of that, so far, actually, these AI use cases have had not that much of an impact on the ISA itself. And this is in part due to the flexibility of RISC-V. People can use RISC-V, use it in many different ways, add custom extensions like, for example, custom matrix multiplication or other AI extensions without having to make them part of the ISA. But on the other hand, now that there are standards in progress that actually do extend the ISA with AI-specific functionality, RISC-V needs to start thinking about trade-offs in this area. And as two people who've worked on the interface of systems and AI for a while, we would like to provide some perspective on these trade-offs. And so the way we're going to structure this talk is that we're going to go through a couple of these trade-offs one by one and provide a perspective on them. But before we do that, I think it's worth taking a moment to talk about the value proposition of RISC-V for AI, because at the end of the day, that's really what is determining these different trade-offs. And to talk about the value proposition of RISC-V for AI, it's important to talk about a concept called the hardware lottery. This is something that our former colleague Sarah Hooker introduced in a paper a couple of years ago. And the idea is that it's an observation. It's that the systems that we use determine the kind of AI that we can explore and build. So for example, it's entirely plausible that deep neural networks are not the only AI paradigm that could have been scaled up to the current capabilities that modern models have, but they succeeded because there was hardware that supported this kind of operation, namely GPUs. And of course, today there is a lot more customized hardware that accelerate the neural network paradigm. But what this also means in turn is that it's entirely possible that there is some research idea, some AI learning paradigm that hasn't been tried yet, but that's also difficult to try out because there's just no hardware available to run it on. And so that's called the hardware lottery. And there are effectively two ways to get out of that conundrum. One is to make it a lot easier to build AI accelerators that are built around entirely new paradigms, or to make existing AI accelerators a lot more programmable, which means that you can try a wider variety of things on those accelerators. And arguably, RISC-V would help with both of them. So let me give you two just hypothetical examples of what this might look like. So imagine that somebody comes up with a new image processing techniques that's a combination of finely interleaving neural network-style compute with DSP-style processing, so that you need to be able to communicate between the two with very high latency. If your accelerator supports doing that DSP operation really close to the neural network compute, you would be able to build this. If you have a long latency between the two, you wouldn't. Another example is, let's say you have researchers who come up with a new type of activation function for a neural network. It's new, so it's not implemented in hardware, so you need somewhere to run it. If you have general purpose compute right next to the neural network compute, then you can use that to do a software implementation of that activation function and try it. Otherwise, you would need to build new hardware in order to support it. And so this is ways in which having general purpose compute intermingled with neural network compute helps you address the hardware lottery. And so this is where RISC-V's value proposition comes in. So RISC-V has a couple of advantages over proprietary ISAs. One of them is customizability. It's very easy to extend RISC-V with new functionality. One is scalability. The same ISA can be used for everything from a very small microcontroller to some large high-performance out-of-order core. And the openness. It can be used with almost no restrictions. And these advantages are not specific to AI, but they are very synergistic because this kind of customizability and general purpose compute mixed with accelerated compute really benefits from this customizability and having a range of different cores that can perform this computation. Is there a downside? There is a downside for existing accelerators because if you do build this kind of thing into an existing accelerator, it means that you have porting efforts and compatibility challenges. But that's not the case if you build something entirely new from scratch. And this is why we gave this talk the title that we did, where we talk about new AI accelerators, because this is really an opportunity for RISC-V. If you build something entirely new from scratch, RISC-V can be very beneficial there. So how do people use RISC-V in accelerators? And I think there is really no single answer, but I want to give a couple of examples how you might go about using RISC-V in this kind of setting. So one is maybe you have some sequencers in your accelerator. Maybe there are controller cores, security cores, boot cores, all these kind of different support processors that are in a modern accelerator. This is one way in which RISC-V might be used in these kind of accelerators. Another one is to use RISC-V as a software fallback. And this is very related to the idea of the hardware lottery that I mentioned earlier. You might have your accelerated compute, but then you also have a RISC-V processor right next to it that can be used to implement things in software that you don't support in hardware yet. And this might be things like the activation function I mentioned earlier. There's another somewhat related case where there is more and more general purpose code that gets combined with AI code. So for example, there is trends around agentic code where the model interacts with some environment and creates an action, and then there's a feedback loop between them. This code needs to run somewhere, and it could be a RISC-V core on an accelerator. That would be more of an AP class core. It probably runs Python. It might run an operating system. And then finally, you have it the other way around as well. You have general purpose cores that might want to build some lightweight ML into a general purpose code that's running. And so having hardware support there built into the RISC-V processor might also be helpful. And this is just a subset. There's probably a bunch more cases of how you might use AI in AI accelerators. And there's an implication of this, because there is no single use case. And this means that if you mandate a particular way of doing AI, it might actually be detrimental to RISC-V, because the benefit of RISC-V in this context is really the flexibility that you can use it in all of these different ways. It also means that it might actually be that the largest benefit you get in this area are all things that RISC-V is already doing. So better single-core performance, we'll talk about that a little bit, is highly beneficial for these kind of operations, particularly if you, for example, offload, have software-implemented versions of machinery operations. Compilation quality matters a lot because you might have compute kernels that you want to run at very high performance, and that depends as much on the compiler as it does on the hardware. And then finally, the software ecosystem is really important. And particularly if you look at these kind of agentic workloads, you really need to run general purpose code, and that is directly related to the software ecosystem. So there are all of these different RISC-V use cases, and that means there is a lot of ways that RISC-V could do to enable them. But it is really important to think about what are the things that really the RISC-V ISA needs to do, and what is the flexibility that it needs to provide to people using them in this context. And this is, I think, where the value, we're thinking about what is the value out of RISC-V and how to enable that is the really important question. And so now I want to go through a couple of trade-offs in this space and discuss where we see that value at. So the first thing I want to talk about is RISC-V and fragmentation in that context. And fragmentation is a discussion that is happening in the RISC-V community all the time, of course, because that's one of the key responsibilities of an ISA. The ISA basically defines a minimum set of standard to make sure that software just works. And by doing so, it ensures that you have binary compatibility, that when you optimize your code, those optimizations carry over between different hardware, and you basically balancing a trade-off where if you mandate too little, then you invite fragmentation because people implement the same thing in different ways. But if you mandate too much, you weaken the ecosystem because you get poor quality implementations or you get poor adoption. And things like the RISC-V profiles basically manage that trade-off by having a sufficiently large set of mandated things that every hardware supports so that software just runs while giving you still flexibility. But what we would argue is that this trade-off looks very, very different for AI Accelerator. And the reason is that flexibility is extremely important, as I mentioned before, but also fragmentation is a lot less of an issue because in AI, typically you have the ML compiler and kernel libraries that map the code down to the accelerator. And binary compatibility is less important as a result. And so that means that not every feature that needs to be necessarily part of the RISC-V standard, just needs to be ensured that the current set of standards support it. And to go into this in a little bit more detail, the way that you typically run AI code is that you have a very high-level representation of it, data flow graph in a language like TensorFlow or JAX or PyTorch. That goes into the compiler, it gets lowered, and at the lowest level it gets mapped down to the hardware. And that means that the binary compatibility is really not needed because the compatibility layer is at a much higher level. And in fact, it may not even be desirable because even if you had binary compatibility, if the way that you implement the hardware underneath it in very different ways, it might mean that optimizations don't carry over. So you might want your compiler to do different optimizations, in which case your binary would look different anyways. And so what we argue here is that in AI workloads only, a certain amount of fragmentation is OK, but it is important that the interfaces are standardized so that things still fit together. And so that leaves us in RISC-V with a balance that the ISA needs to strike. So on the one hand, you could imagine where you have one AI standard that mandates exactly how you implement a particular AI feature, like, for example, this is how you implement embeddings, this is how you implement matrix. This is basically what every RISC-V binary needs to support. But that reduces the opportunity for differentiation. So for example, if I come up with a new way of doing a particular AI operation that differs from what's in the standard, then it's very difficult to balance those two. On the other hand, you could also have an environment where everything is entirely restriction-free. Then you get the freedom to build all of these things, but then you make it difficult to compose AI ideas in IP. And so RISC-V does need to find a trade-off in this space. But we argue that for AI, this trade-off probably looks different and probably errs more on the side of providing flexibility and avoiding the risk of baking assumptions into the ISA, which, as I mentioned with the hardware lottery, may not hold indefinitely. OK, so I talked a little bit about flexibility and fragmentation, but let's talk about what that means for the IP ecosystem and reuse versus customizability of IP components. So, as I said, the compiler helps bridge the gap from the software down to the hardware, and binary compatibility is less important. But that doesn't mean that you don't need a layer of compatibility. And this is so that you can mix and match. So you still want to be able to have interoperability between different IP blocks and mix and match functionality together. So if you don't have any standards whatsoever, you would have standards that basically try to interact with the same components in a different way, and so they're not composable anymore. Now, there are different levels at which this happened. One is it happens between IP blocks at the chip level. And it also happens when you try to integrate custom AI functionality directly into the CPU, which is some of the use cases I talked about earlier with the hardware lottery. So let's talk about the first one. The first one actually looks very similar to what RISC-V is already doing today. You ideally want an ecosystem where you can just mix and match IP, plug it together in the same network on chip, have cache coherence between them. There might be one difference between AI workloads and other workloads in that interrupt handling might be less important for AI workloads because you typically know how to sequence these workloads before you schedule them. But this is basically the integration model for a lot of the use cases I mentioned earlier. And effectively, RISC-V is already doing the right thing in this space. The area that becomes more complex is what to do about AI functions. And I'm going to use matrix multiplication as one example here, mainly because it's something that I think lots of people have thought about. But this is basically applies to any AI functionality that one might want to integrate into a RISC-V processor. And effectively, this trade-off space has three options. So the first one is you don't define anything at all. So different vendors can define different matrix units. They have different interfaces. They plug into the existing IP in a different way. And there's no way to mix and match them. The other one is that you basically add the functionality to existing RISC-V standards. So for example, you could build everything into RVV, but then the risk is that everyone who implements RVV needs to implement the standard, and if things shift in the future because new AI paradigms emerge, then the ISA is stuck with them. And then there's a third approach where you basically say, let's not standardize, in this case, the accelerator itself, but let's standardize the interfaces. So there's already interfaces that allow you to plug for custom logic into things like the register file. V6 is one of them. There are a couple of them. And what this allows you to then do is to be able to mix and match this different IP while having complete flexibility of how you would implement this. And so we think a risk here is to be aware of the fact that by standardizing things, we might lock things into a particular paradigm that may not hold in the future. Does that mean we shouldn't be working on these standards? We should totally be working on these standards. I think it's important that there is functionality, like, for example, matrix multiplication available for RISC-V, so that somebody who just wants to take RISC-V IP has a default that they can fall back to. But we think the standards should be implemented in a way that they can be optional and that they don't preclude customization. So for example, you should be always able to take that standard out and put a different standard in, and it shouldn't give a disadvantage. It should basically all be able to go through the same interface. This is mostly related to register-based interface. There's another interface that we think is worth for RISC-V to think about, which is that AI workloads often need to dispatch parallel work to different units. So for example, you have multiple MSUs, you want to dispatch work to all of them at the same time. And in RISC-V, this currently doesn't have first-class support. And so this might limit some of the use case of RISC-V as a sequence in those scenarios. And I think an interesting question is, should RISC-V have an extension for this? And it could take all kinds of different shapes. It could be VLIW-like, it could be a decoupled vector fetch architecture, or something more like DMA. There's lots of different approaches here, but it might be worth for RISC-V to think about this one. And then finally, an area that I hinted at before and that I want to talk about as well is the role of high-performance CPUs. So I think there's a perception that the most important thing for an AI accelerator is the ability to run, say, neural network compute very, very quickly. And we argue that for RISC-V, it's also very important to have high-performance CPUs. And here's the reason why. So when we go back to the example from earlier, where you address the hardware lottery by having a RISC-V processor be the software fallback for the hardware accelerated functions, your CPU needs to match the throughput of that accelerator block. And so as the throughput of that accelerator block increases, the CPU also needs to be able to catch up. And so AI workloads are also becoming more dynamic and burstier, which means that IPC matters a lot for that. So single core performance is very important. Some operations might be parallelizable, but single core performance remains very, very important for these use cases as well. And then this one is a trend that I think is happening in the AI community more broadly. AI workloads are increasingly starting to mix general purpose compute and AI computation into combined systems, where you have a portion that's really a general purpose, say, agent environment, and that goes back and forth with the model. And that also tends to be code that's limited by single core performance. And going towards multimodal models that are looking at things like video and images as well, just increase that trade-off further. Of course, the RISC-V community has been doing a lot of work towards high-performance CPUs. There is now a wide range of IP available. But at the very, very high end of performance, I think there's still a perception that there is no obvious RISC-V contender available yet. And the case that we want to make here is that such a high-performance CPU would not just benefit HPC and general purpose workloads, it would also benefit these kind of AI workloads. So we basically, in this case, want to argue high-performance IP that has these kind of standardized interfaces to plug AI into it are really one of the things that is very, very important for AI workloads. And with that, I'll hand it over to Cliff for the second part of the talk.
Thanks, Martin. And let's take the change time to say, if you're packed in the back, feel free to file in. There's space along the sides and maybe a few seats, so you don't all have to bunch up in the back of the room. So I thought I'd touch on a few more particular themes, one close to implementation, one at the border of hardware and architecture implementation and neural networks, and then diving more into the models themselves. So the one that's closer to home is many-core versus single-core. Some of you probably read the TPU papers. One of the delightful and surprising things about TPU v1 is that it's a single-core chip. You know, it was 2013, so it's 10 years ago, but we're well into the many-core age at that point. TPUs have stayed small number of cores, depending on how you count 1 or 2 major cores per die with a little bit of garnish for sparsity and so forth. Other people have taken very different approaches. Facebook's, Meta's MTIA is 64 cores per die. GPUs, if you think of an SM as being like a core, are well over 200. And so they're deep into many-core territory. And so I've shown that schematically with a little loopy arrow as sort of a thread or a core here. These architectural choices, in some ways you could say, okay, those TPU guys have weird religion and they're building very few cores per chip, but these have implications for the performance of your system in terms of how memory works and how the NOC works. Also how easily you can program the machine. So I will personally report that programming a single thread of control in TPU v1 was a delight compared to the usual software engineering tasks of I got a huge number of cores and I gotta lock them and I have to coordinate all of their loads and stores to memory so they line up in the cache just so and get my prefetches to match this. It's a discipline to get your many-core general purpose machine to screamingly fast process things, but like if you have a single core, you might not have to do that. Also, the memory systems of our CPUs tend to be 64-byte cache line based. The memory systems of our accelerators are often broadside, like kilobyte or multiple kilobyte per cycle motion, right? Take HBM at 3 terabytes per second, divide that by your clock rate. How wide is that bus? Do you want to take that kilobyte per cycle and then parcel it out into tiny 64-byte chunks, or should you keep that beautifully coordinated parallel load and use that to feed your beautifully parallel coordinated compute unit? Maybe there's some sort of matching there. Google also, in terms of that single or few core bet, has gone with gigantic systolic arrays. I think other people are inching up in the sizes of their systolic arrays. We've placed a bet, and it continues to work really well for us with that large systolic array. Systolic arrays come with this benefit that I think we emphasized in that first paper about reuse, right? Because the dimension is large, you just get that dimensionality of reuse for each of your arguments flowing through the array. And that reuse is wonderful from an energy perspective, power perspective, how you get your work done in perspective. There are, of course, corner cases. If your batch size gets really low, you got to play other tricks. We can talk about that offline. The flip side of this, though, is if you bet on the many-core direction, and I think that's a good systems bet, right? Like, we know how to make many cores. We have NOCs we can buy off the shelf, and we should use those. But if you're going many-core, how do you re-attain that reuse, right? You got one chunk of memory, and you want to send it now to 64 of the cores on your chip. Does it just land there, or does some other mechanism get it there? There are tantalizing hints in some of the other accelerators design sketches about read multicast, but I think the usual path is one core fetches and maybe it hits in cache, and then if you're lucky that the item stays in cache and the other 63 cores then go and hunt for it, and whether they hit or not, it might be luck. A little more coordination among your cores, a little bit more thinking about what you really love to do is multicast. Read it once, send it to 64 destinations. Can you get that out of your interfaces? Not a standard CPU thing, but an area where if you're going multi-core, pay some attention. All right, takeaway. There are natural strengths for RISC-V ISA in the single core, like a TPU, although I'm not talking about Google products, and controller cases with multi-core, which is where a lot of us are going to go if we use RISC-V. Be careful about that sharing thing. Don't forget it while doing your system design. Part 5, second of my points, kind of on the boundary of implementation and machine learning. Numerics. I asked Sami Bengio once, a colleague at Brain, like, I'll bet you think you're using a real number. And he said, yes, I think I'm using a real number. And in fact, like, we give him horrible floating point things that look like this. I stole this slide from the wonderful work by people done at OCP in the MX Alliance. It captures bits we use inside a single data item and sort of metadata bits about scaling factors and so forth. There's a plethora of different things. The people working on this are basically playing Jenga with the bits of our numerical representations while still asking, will it train? And will it still preserve accuracy when we infer? Because we want both of those to happen, and the formats are not necessarily the same. I think the takeaway from the slide is, wow, That's a lot of slightly different hardware implementations with multipliers and adds to go with them. Really, quite a few. And then let's bring this back to RISC-V and say, do you think SEW, which can encode multiples of 1 byte, is going to finish the job for us? I think we need a little more than what SEW gives us, right? Like, we're below 1 byte. We're into 6-bit and 4-bit formats here, and different interpretations of those 6-bit and 4-bit formats. So I think we need some other way of capturing the standardization in numerics and expressing it so that we can put it into maybe architectural extensions or maybe some sort of space where we fill things in. We need this flexibility because the target is moving, right? The numerical representation is not sure. We're going to knock out as many bits as we possibly can in the name of efficiency. Another way of calling this is EXMY, number of exponent and mantissa bits, although that doesn't capture the scale factors. I said target is moving rapidly. Yeah. The other thing is there's those out-of-band values, the things that are not in the per value thing, like there's scale factors or sub-channel scales or whatnot. Where do those get stored? Where do those end up in memory? Your beautiful power of 2 byte memory system is going to get jiggled a little bit by having to move those metadata scales and shift factors and so forth. So think about that as far as tensor layout. And be super careful about standardization efforts, because if you say, well, I can fit anything that's a power of 2 bits, you might mismatch with where the technology is going. So numerics, moving target, really fun things coming at us as we figure out what are we actually differentiating here and what's actually fundamental in these networks. I don't think we're nearly as efficient as we could be, and there are going to be algorithmic and numerical breakthroughs that change the game for us. So if we bake the snapshot from today, we're going to be sad in even 5 years rather than 20 years from now. A little bit of visitation of neural network models. So if you take your time machine back to AlexNet, a lot of the stuff that's in AlexNet is still very much alive today in blue, right? The blue stuff, fully connected layers, convolutional layers, pooling, normalization, softmax, ReLU, activation functions, they're all there 12 years ago for AlexNet. There are a few new things. We added element-wise operations to do LSTM gating. They're alive and well in various different residual functions. Embeddings weren't trumpeted so much in AlexNet, but are actually a huge part of recommender systems and today's transformer-based networks. There are new activation functions, and of course, attention might be all you need. That is certainly where multiple billions of dollars worth of investment are chasing whether attention is in fact the last hardware ingredient we need to power this great AI revolution. I will say, playing, I don't know, devil's advocate, heretic, something like that, are you completely sure that attention is all you need? Are you sure that we have the last mechanism to get ourselves to mimic natural intelligence in our artificial general intelligences? Because there seem to be some holes in what biological or natural intelligence do compared to what we get in our AGI systems right now. And you guys know all the issues. Of course, we are concerned about factual grounding and alignment and basically applied ethics. Like, we can barely get people to be ethical, so how do you expect to get the machines to be ethical? Will there be another mechanism? It seems like a bad bet to say there will not be another mechanism. In particular, I think I want a personal medium-term memory, right? The context window is a short-term memory. The weights are instinctive or maybe reflex-like operation. Where is the medium to long-term memory? Maybe we'll get it with some of the things that are like increased context length, which many companies, including my own, are pursuing quite aggressively. Maybe we'll get it with retrieval augmentation and retrieval augmented generation, right? Take another, maybe more traditional computer science system, couple it to your ML system, have them talk to each other, and augment each other, possibly factually ground each other. There's other interesting questions about multimodal. I think I mentioned, no, I didn't mention reasoning. That's one of the hot things. Let me leave that for Q&A time. One of my personal quests is the sparsity side. Of course, there are more versions of sparsity than there are sparsity experts, so be very careful when you say sparsity, but it is one of the ways into incredible efficiency. So my bet is that attention is unlikely to be all that we ever need, which means we'll need somewhere to stand, some sort of insurance policy, a backstop which is probably programmable, a little bit flexible, probably has throughput that is within an order of magnitude of our massive accelerators. If it's all accelerator and no flexibility, that's a kind of precarious, dangerous bet. I hear about startups that have a plan to specialize to the transformer. And I worry a little bit whether that in 5 years will look about as good a bet as going all in on SRAM and no other memory, which has not necessarily aged well in the era of giant models. So, rhetorical question, what components might still be missing in our universe? All right, takeaway. Algorithmic advancements continue. This is actually a joy of the field, right? Like, it's not, we had one breakthrough in the last 10 years have been just making AlexNet work. Every year, there's a new breakthrough, a new technique, a different numerical representation, and that changes the game, which means our target is moving, and us computer architects who are building machines for this are still in business. So please, neural network researchers, keep up the mutation rate because it makes our jobs fun and complicated. Last bit, and then we'll take questions. Various calls to action. I think part of what we're saying here is let's exercise careful taste. And of course, we all have definitions of what constitutes good taste, but sort of the right balance of standardization, so we have a common platform we all can build upon, but not premature standardization, because if we place a bet that nobody wants to use or hasn't been proven in like battle testing, marketplace use, then we might regret it, and that will be a weight around the neck of the architecture. One way to get at that is interfaces. I think Martin had a really nice statement about standardize or leave as the Wild West, or can you build interfaces which don't specify implementations but allow a variety of different implementations under the expansion interface, the maybe co-processor interface. Martin spoke to high-performance cores. Small chance to proselytize. 20 years from now, do you think the current split between how we do machine learning and how we do traditional computer science will still hold, right? Machine learning is differentiable, continuous, real-numbered. Classic computer science is branchy, loady, discrete, integer. Do you think that split stays? I can't imagine that 20 years from now that stays. I think the two fields will fold back together. How are we going to do that? We're going to need general-purpose cores really close to these accelerators, and they're going to have a very closely coupled dialogue. It feels inevitable to me, but please feel free to argue with me in the hallways about it. If that's inevitable, then we need the high-performance cores that Martin was arguing for to hybridize with our machine learning accelerator units. Two well-established pathways, of course, we have an ISA, you can lean on that. We have extensions that are optional. You can start to lean on that and share work with the other people who build that extension. We have a software ecosystem that we're building and making better all the time. And how easy is it to pick something up? I think, do you have to download the Berkeley GitHub repository and then like call up the graduate student to get your thing to work? Or is there a container that just like snaps into place and things work remarkably well? That kind of pathway, ease of use thing we have to invest in. And I think I mentioned software ecosystem. So let me pause, having run a little bit into the Q&A time, and let's switch into interactive mode. Really great to have everybody in the room. Can't wait for the follow-up conversations. Thank you.
Thank you, folks. So questions, hang on.
Oh,
Waiting for the
microphone coming to you.
Yep.
Hey guys, so to Martin's points, I just want to put in a small plug for the new Composable Custom Extensions Task Group that we've just started. Our task group's goal is to greatly enhance RISC-V's lead in customized computing. We're delivering a hardware-software framework that makes it possible for anyone to create and reuse new extensions that compose together in a system. It's a hardware-software perspective, so we will have APIs, we'll have standard extensions that allow you to compose custom extensions and share that custom opcode space, and we expect to have hardware logic interface interop standards so that you can have modular hardware accelerators that plug into the framework, kind of like what Martin was talking about. So we're brand new, we're in the plan milestone. Join our mailing list, participate, and help us build some of these interop standards so that you can build just these kinds of AI accelerators that work together. Thanks very much.
Love the effort. Can I tweak you for, was there a question there? I think Brian raised his hand, but is far away from the microphone. Like,
Yeah, hang on. Okay.
So you mentioned that numerics are moving really fast and an area of interest. This is an area that I am weak in and thus would love more thought from you, because like the posit extension is one that I was reading about recently. It was blowing my mind. What numerics extensions and new pioneering things are exciting y'all?
Okay, so the MX Alliance is the solid multi-custom company OCP work that has a bunch of great proposals for standards and training recipes and so forth. They're probably the closest to a consensus source of goodness around this. We watch them very carefully and like the work that they do. Numerics as a field is poorly documented. I wish Kahan had written his thick textbook. He never did. If you go to his website, it's kind of oracular little sayings. There's a lovely introduction to IEEE floating point by, is it Singleton? Overton, I think. I'll have to dig that up. That is basics, more scientific computing oriented. Part of the problem is we're inventing new math here, right? My friend Sammy said, I think I'm using a real number, and we're blasting away at the real number. When you're down to 4 bits, there's 16 representable values. Are you really multiplying or adding, or are you just doing lookup tables? How much of that you need to master is a question. I think really what you're using it for is an interesting question. So a bunch of the stuff that the POSIT and HPC communities are wondering about is, will this matrix still invert, or what happens at this poor condition number limit of things? Our ML colleagues are way more practical about, does it train? Do I preserve recall on inference test things? So it kind of depends on how practical versus a numerically theoretical thing you want to do. I find the numerics part to be really rich and fun, even though I'm still a dilettante there. So I happy to point you at books that are just unbelievably deep about this kind of stuff.
I would add one more thing to this, which is that there's actually something on the interface side as well that's very related to numerics that I think we're all used to thinking of interface in terms of there is a data type, and that goes across the interface. And if numerics are the thing that you actually want to swap out, that actually breaks the interface a little bit and might mean that we need to build different interfaces than we did before.
Hi, Cliff and Martin, great talk. My question, you mentioned 2 things. One is, or 2-part question. One is you mentioned you don't want to lock people into one type of memory. Specifically, you mentioned SRAM. So my question is, what different kinds of memories do you envision as the RISC-V ecosystem evolves? Are there some guidance or visions you have of how the memory subsystem and memory types need to evolve? And then are there other innovations in memory? Like we're seeing it, at least you mentioned OCP. OCP put out a spec for compressed memory, at least for CXL memory, and NVIDIA implemented decompression. So any thoughts on emerging memories and memory architectures for AI, and then also for some innovations like compression, or maybe there are other innovations we haven't thought of that you see would be great in this RISC-V ecosystem?
Maybe to question 1 about SRAM. I wasn't knocking SRAM. We wouldn't live without SRAM in our machines. Just that there was maybe the first round of AI startup hardware companies bet on heavy SRAM, maybe even no DRAM in their architecture, and that has not aged well as a bet. I don't think that's a terribly controversial statement. It was, but we absolutely need SRAM. To your third question of what memory technologies, we wish we had better SRAM. SRAM is not scaling with process node generations, and so the amount of SRAM we can fit into a chip is not keeping up with the number of compute transistors we can put in. No magic physics bullets coming that I can see. AMD has die stacking for some of their caches, which helps a little, not necessarily great. One other religious point is, do you build a cache memory hierarchy like your CPUs know and love, or do you build a scratchpad hierarchy like TPUs and other accelerators use? Kind of a compare and contrast. How close to general purpose do you need to be? How much are you willing to invest in your application code, managing moves through the scratchpad memory hierarchy where you control everything, but of course then you have to write everything? That is a balance that we strike in accelerator design.
And then adding to the second question, I think I wouldn't think as much about it in terms of what are the things that are likely going to happen in the future. I think the one thing that's certain is that we can't really predict it. So I think from a RISC-V perspective, I think the ISA should anticipate that things can change a lot, but it's difficult to anticipate how they're going to change. So I think being prepared for whatever the paradigms might become important in the future is probably the best thing I think RISC-V can do.
Hey guys, I'm a Zoogler. I worked on the Jellyfish, the early generation TPU. You talked about high performance computing and the thoughts around, AI/ML acceleration units, right? I was wondering if you had any thoughts on, going into the future, the nearness of the storage and what implications the distance of the storage might play. in this whole sort of solution scenario?
Which storage? Do you mean like spinning Rust, or do you mean flash drives, or do you mean
Flash
DRAM?
drives. I mean, the data sizes are very, are you loading data half the time, or are you, choked on the compute side, or are you choked on the training side?
I would say network and memory are our worst, or network and memory bandwidth are our worst problems today, much more than compute. It's relatively easy to add compute to our dies, even though we're at kilowatt power dissipation. The HBM technology, which is the best off-chip DRAM we can get, never gives us enough bandwidth, right? We can never put enough stacks on the shoreline of the chip. And the interchip interconnect, which is like NVLink, the proprietary scale-up interconnect, uses all the wires that we can connect into the chip. And it's still never as much as we'd like to have, and never at the scale that we'd like to have. In some ways, like, maybe we should have put this into the talk. Like, worry less about the compute. Worry about the choreography of tensors into and out of memory and across the network on your machine. That's the really hard problem.
Okay, thank you.
Okay.
Just a quick add. I was at the TSMC OIP conference here a couple weeks ago, and a very famous professor from Stanford, can't remember his name, but he gave a whole thing on the future of where computing is going. And on this whole memory thing, I can tell you that's a major focus, and the stacking is, there's new materials coming is the bottom line. So the first week of December, there's a conference out here, I think IDEM or something, that's going to be talking a lot more about this. And one of the biggest problems has been with silicon and the metal, we can't really stack chips very well, or layers. So you got to have all the metal above all the NMP transistors. And with some of these materials coming, they can be below 400 degrees C, which means you can now intersperse metal layers between the different transistor layers and truly enable some pretty large stack-ups and new memory technology. So I think that's another thing. RISC-V may not do anything. We just need to be aware of some of these material changes coming.
Was there a question?
So I think we have time for one more question before lunch. And who is going to be the one holding everyone here for one more minute? Any questions? No? No question? Okay.
So I guess, Martin, my question is your approach, which is instead of trying to standardize the IP, you want to standardize the interface to the IP and then leave the door open for innovation. So is there like in terms of interface, could you elaborate what do you mean when you say interfaces? Is it just the register interfaces to kind of control and telemetry and things like that, or you mean something more than that?
So I think there's going to be at least a couple of interfaces. So one is, I think, going to be the vector register file. That's the example I mentioned in the talk. I think getting to the regular register file, getting to the memory system, that's another one. And then basically the kind of parallel dispatch interface. I think this is a subset of them. There's probably also something around getting kind of out-of-band information to different components, like Cliff talked about the numerics, keeping that as an additional communication path. And then maybe also something around discovery. So there's probably a couple of different standards that would be needed for this, and I think they would need to closely integrate with AI standards that are coming out. And I think the thought experiment when designing these standards will basically be what is the weirdest design I can come up with for this unit, and would it still work? And basically, I think that's a good test to run.
Maybe to add on to Martin's response, in the CPU area, we have a number of great ways to connect cores together, including incoherent or coherent shared memory, various different locking mechanisms, which might be supported by atomics in the ISA, interrupt and exception mechanisms. We should reuse all of those as much as we can. And then we should also be willing to consider things that are the moral equivalent of scratch pads. Like it might be that some combination of MTI accelerators should be bound together with something which is not in the previous tool set, because we know how to make it work in the combination of software and hardware to perform for the particular applications we care about. We should be open to that possibility, but should you standardize it right out of the box, or should you play with it and understand the capabilities before you propose standardizing it? I think certainly the latter.
You mentioned a bunch of dimensions to improve performance, parallelism being one of them, a different and orthogonal dimension. Speculation, does that have any place in AI?
So far, not much. I joke that we can predict our TPU's branches 2 months in advance. And
However many there are.
yeah, and so it feels like there are places where things might move, like in some of the mixture of expert computations. There's stuff that looks like routing. You don't actually have to implement it like routing. You can parallelize differently, and then there's no routing in it. But that has the possibility of, could you speculate? But so far, we have so much work to do that it doesn't feel like doing extra work to try to get ahead is the likely path to win. We're still behind on the gigantic models that we do want to do.
Jeff Dean gave a great keynote at MLSys a couple of months ago. It's online, so if you look that up, he talks about some of these things.
Any more questions? I know you are eager to ask one more question. No? I think that's it. Thank you very much, folks.
Thank you.